We're continuing with chapter 5, which is on trig identities. In this video, we're going to go through section 5.3, where we're going to see how the sum and difference identities for cosine are derived. But also in this section, we're going to use the sum and difference identities for cosine to derive the cofunction identities. So if we take a look at the trig identities sheet, okay, up to this point, we've looked at here are the fundamental identities. These are the trig identities we've covered so far, but in this section, we're coming to this sum and difference identities category, and in this video, we're going to focus on the sum and difference identities for cosine. So you can see plus or minus, this includes both the sum and difference identities of cosine. And then in the next section, we're going to look at the sum and difference identities for sine and tangent. And then if we come down here in this video, this section, we're going to be talking about the cofunction identities. Now, if you remember, we've actually already talked about the cofunction identities at the start of chapter 2. So in chapter 1 and chapter 2, we actually did derive some trig identities. We derived the quotient identities. They're calling this the tangent and cotangent identities, but they call this the quotient identities earlier. We derived the reciprocal identities. We derived the Pythagorean identities. That's why in this chapter we didn't go through these again. We already derived these earlier. But around that same time, we also did look at cofunction identities, but we never stated explicitly, put an official box around these and called these identities at that time. The reason was because for what we developed, the domain, the inputs into the identity for theta were strictly acute angles. And so what we're going to do in this section is we're going to prove these identities for the more general case of any angle theta, any real number theta. Okay, but let's go back to the beginning of chapter 2 and review what we learned about the cofunction formulas at that time. Okay, so cofunctions. The idea was you could construct any right triangle like shown here. This represents a complete general right triangle. So angles capital A, capital B, capital C, and then the sides opposite those angles. This is like lowercase b, lowercase c, lowercase a. Okay, and with that, if you think about evaluating the trig, or trig function of the acute angles, capital A or capital B. So the sine of capital A is opposite over hypotenuse, A over C. But then what would be equivalent to, what trig function would we need to take of angle B to also get A over C? Well, that would be cosine of capital B. So sine of capital A is equal to cosine of capital B because both are A over C, right? So they write this here. And you could do a similar process of equating a trig function of angle A and angle B. You could do that with tangent and cotangent and secant and cosecant. All right. Now, with that, they note how for any right triangle, the two acute angles are going to be complementary. They're going to add to 90 degrees, right? Because the sum of all the angles in any triangle is 180. Well, with a right triangle, one of the angles is 90. So that means the other two must sum to 90, so they're complementary. So that means you could say that so if A plus B, they're complementary, so A plus B is 90. So you could say A is 90 minus B, or B is 90 minus A, right? So with that, you could take any of these three formulas and make it and have it represented in terms of one angle, either angle A or angle B, because you could just convert the other one to, you could convert B to be in terms of A or A to be in terms of B, and now you've got this trig identity, right? You could say tangent A is equal to cotangent of, it would be what? It would 90 minus A. Or you could say tangent of 90 minus B is equal to cotangent B. And that's the cofunction identities, right? If you come here, there they are. They do it, so they say sine of A is equal to cosine of 90 minus A, but then instead of putting B, they just use a single angle, right? You could replace A with theta. And so, like we would say, so here, sine of A is equal to cosine of 90 minus A, but instead of saying sine of 90 minus B is equal to cosine of B, you could just write that in terms of A as well. sine of 90 minus a is equal to cosine of a. Same thing. And so that's the 6 cofunction identities. Okay, but you can see though that these are derived where it says for any acute angle a. And so we didn't put an official, put these officially into the trig function sheet, trig identity sheet, because when you think of the identities, they're valid for any angle, not just like a restricted range of angles. Okay, and then the way that another way of looking at this is that it says the cofunction identities state the following: cofunction values of complementary angles are equal. So yeah, you think about cofunction pairs. You could write these equalities in terms of the acute angles of a right triangle. You could write those equalities with sine and cosine, tangent and cotangent, secant and cosecant. But you couldn't do it with like cosecant and cotangent or secant and cosine. It was strictly sine, cosine, tangent, cotangent, secant, cosecant. And so if you have a cofunction pair and you've got two complementary acute angles, then you could set those two equal to each other in terms of the sine of one of the angles is equal to the cosine of the other angle, or vice versa. That's the idea. All right. Okay, so now with that, let's take a look at section 5.3. All right, the difference identity for cosine. So you have, several examples presented earlier should have convinced you by now that cosine of a minus b, so that's the difference identity. We're looking at in this section, what is cosine of a minus b equal to, and what is cosine of a plus b equal to? That's the difference in some identities. But we know that, so cosine of a minus b does not equal cosine of a minus cosine of b. I think our intuition up to this point would tell us that, and they go ahead and they say, okay, what if a was equal to pi over 2 and b was equal to 0, and they show that this is not true. And that's just one case, so maybe it's true for another case, right? Maybe you pick another a and another b, and then cosine of a minus b is equal to cosine of a minus cosine of b, but then that wouldn't be an identity, right? I mean, I guess maybe it could be true for a certain restricted range of inputs, but that's not the way we're looking at the trig identities. All of these are valid for any input theta, as long as it's not like, if you put a quadrantal angle for cosecant or something, one of the quadrantal angles where it doesn't exist, but if it exists, it's going to hold true for any theta that isn't a domain restriction. Okay, so now to derive a formula for cosine of a minus b, it says we start by locating angles a and b in standard position on a unit circle with b less than a. Let S and Q be the points where the terminal sides of A and B respectively intersect the circle. Let P be the point 1, 0, and locate point R on the unit circle so that angle POR equals the difference A minus B. So, okay, to summarize what that paragraph, you got a unit circle here. Okay, so we're going to be thinking about the unit circle definition of the trig functions. They take an angle. So in red here, this terminal side represents angle A. This terminal side represents angle B. Oh, no. Sorry, B is less than A. So this terminal side represents angle B. This terminal side represents angle A. Okay, and then this terminal side represents angle A minus B. So you can think about this is, you subtracted B from A. So this is B. Right? And then it says, so the point where the terminal side intersects the unit circle, for angle A, that's point S. For angle B, that's point Q. For A minus B, that's point R. And then the initial side at the standard position is point, intersects at point P. That's at 1, 0. Right? It's because it's the unit circle. Okay. So with that, what they then do is they note that angle ROP is equal to angle SOQ. And, you can think about that being true because it's like if you took this and kept it rigid, and you just rotated it, and you rotated it through angle B. Well, you're going to rotate it to here, right? So you haven't changed the angle between these two lines, okay? And then let's see what else. They note that, yeah. So also note that with the unit circle definition, we know that with the unit circle simplifies trig function values because the coordinates of these points are based on just sine and cosine of the angles. So this is the coordinates of point Q is cosine B sine B. The coordinates of point S is cosine A sine A. The coordinates of point R are cosine of A minus B sine of A minus B. That's this angle, right? And then the coordinates of this point are just 1, 0. Okay. Let me copy this. Okay. So now, because these two angles are equal, and which you can think about, that's just like a rigid rotation of this B around the unit circle, then these chords here, from the chords SQ and the chord RP, are equal in length. And they state this here, that because the central angles are equal, that from geometry, that's more of an official statement, math statement. If the central angles are equal, that means the chords are going to be equal. Okay, so with that, you can use the distance formula, but the distance between 2 points in the Cartesian plane, right? So like y2 minus y1 squared plus x2 minus x1 squared, the square root of all of that. And we can use that with the coordinates that we get because of this unit circle definition. We can set these two chords equal to each other with those coordinates. So they apply the distance formula to both chords and set them equal, and they get this. So there's the distance formula, right, from algebra. Then, okay, they then square both sides of the equation, which gets rid of the radicals, and then they're left with, yeah, just they got rid of the radicals, and then they're going to expand out these squares here, and they note the formula for the difference, the x minus y squared, like you get this perfect square trinomial formula, and so they expand it all out. Okay, then they note that the Pythagorean identity sine squared x plus cosine squared x is equal to 1. And so with that, like you have cosine squared of A minus B plus sine squared of A minus B. That becomes 1, right? 1 plus 1 is 2, so you're left with 2 minus 2 cosine A minus B. Here, there's cosine squared, there's sine squared of B, there's cosine squared A plus sine squared A, so they could bring all that together, and they're left with this. Okay, then they factor out a 2 here. Or is that what they do? No, you subtract both sides by 2, and you can divide both sides by -1, and you're left with, there's the difference identity for cosine right there. Cosine of A minus B is equal to cosine A plus cosine B plus sine of A, or is equal to cosine A times cosine B plus sine of A times sine of B. So this is the identity for cosine A minus B. Although figure 4 shows angles A and B in the second and first quadrants, respectively, this result is the same for any values of these angles. Yeah, so this is completely general. This identity holds for, you can input any angle A and B. And so that's why we officially put this into our trig identities sheet. Okay, now the sum identity, so what is this, right? Is, I'm sure you could go through another derivation, just like a similar derivation like we just did, but an easier way is to say, so plug into the difference identity, plug in just A, but then also plug in minus B. So for cosine of A minus B, we're going to say A is just equal to A, and then B is equal to minus B. So what happens is you get A minus B is cosine of A plus B, right? And then you're left with, so cosine of A, cosine minus B plus sine of A, sine of minus B. And you can use the even odd identities for sine and cosine to simplify sine of minus B and cosine of minus B. And that's what they do. Sine is an odd function, so you get sine of minus B is minus sine of B. cosine is an even function, so cosine of minus b is just cosine of b. And there's the sum identity. All right, and so with that, there is where they officially state the cosine of a sum or difference. Okay, so it says these identities are important in calculus and useful in certain applications. For example, the method shown in example 1 can be applied to find an exact value for cosine of 15 degrees. So yeah, you use the sum and difference identities. You use all of the trig identities for different applications in calculus and just other situations. But it talks about here that we can now use, we can take these trig identities and use them to find exact values of other angles. So if you remember in chapter 2, up to this point, we only have exact values for trig angles for trig functions of angles for the special angles, which were 30, 45, and 60, and the quadrantal angles. So like we know cosine of 0 is exactly 1, but outside of the quadrantal angles, we only know exact trig function values for the special angles 30, 45, and 60, because we could use geometry to find this is 30, 60. We could use geometry to get these side length ratios. Right, but for other angles, there's no way to get the exact value. And so to get values of other trig functions, you just use like a numerical method using the definition of the trig functions, and that's what your calculator is doing in the background. When you say cosine of 10, well, that's the exact value, so you have to get that as a decimal, right? As opposed to if you said, whatever, sine of 30, I'm in degree mode, yeah, it gives you the exact answer, right? Because sine of 30 is opposite of hypotenuse 1/2. But now with the sum and difference identities for cosine, that opens the door to find exact values of other angles outside just the special angles. So they say, okay, here, what is cosine of 15 degrees? So you can write 15 as 45 minus 30. And so with that, you can put that, so that means cosine of 15 is equal to cosine of 45 minus 30, right? But then you apply the difference identity to that, and there's an exact value for cosine of 15 degrees. And so if we come to the calculator, there you go. It gives you an exact value. And then they also do this for, so cosine of 5 pi over 12, 5 pi over 12 times, okay, so we got pi radians. 180 divided by 12 is 15. 15 times 5 is 75. So, yeah, they do the same idea to get, so 75 you could write as what? That would be 60 plus 15, or you could do, let's see, because we just found 15, right? So once you have an exact value of a trig function of an angle, then you can use that, that now you have that to use with the sum and difference identities. So 60 plus 15 is 75. I guess you could still get the 75 with, so 45 plus 30. Yeah, you could do cosine of 45 plus 30. And so you get this. And so if we plug in, we could take any trig function, 75. There you go. It gives you an exact value. Now, it only works out to where it's not like you can just, now you can get any angle you want just by putting any kind of sum together, because if you think about it, this is only going to open the door for exact trig function values of any angle that's a factor of 15, as far as we're talking about degrees, a factor of 15. So 0, 15, 30, 45, and just going up in 15, if you put that into your calculator, it's going to give you an exact value. Okay. Now they show here that you can go the other direction. So this is pretty complicated, right? Looks pretty complicated, but if you look at it as in terms of the sum identity, then you can combine this as this is just cosine of 87 plus 93. That's cosine of 180. That's minus 1. So all of this is equal to minus 1. So you can go in the other direction as well. You can see an expression and say, hey, I can combine that into a single concise trig function using the sum identity for, we're talking about cosine in this case. Okay. So now let's take a look at the cofunction identities that let's prove the cofunction identities for any input angle, not just the acute angles. So we can use the identity for the cosine of the difference of two angles and the fundamental identities to derive cofunction identities presented previously for values of theta in the acute angles. For example, substituting 90 degrees for A and theta for B, and the identity for cosine of A minus B gives the following. So yeah, what is cosine of 90 minus theta? That's a cofunction identity, right? But let's put this into the difference identity for cosine. So they do that, and so cosine of 90 is 0, sine of 90 is 1, and they're left with sine theta. And so there you go. We know that we just used the difference identity for cosine, which we know is true for any angle theta. And so now, if cosine of 90 minus theta is equal to sine theta, we prove that using the difference identity for cosine, then now we can state this as an official cofunction identity for any angle theta. And that's what they state here. This result is true for any value of theta because the identity for cosine of A minus B is true for any values of A and B. Okay, now from there, they just go ahead and state the rest of the cofunction identities. I'm not sure why, I'm assuming that so we're going to learn the difference identities for sine and tangent in the next section, and I'm sure you could use those identities to prove the cofunction identities for sine and tangent. But then there's also secant, cosecant, and cotangent, which we're not going to learn any sum and difference identities for those. So we'll see as we progress through this chapter. I'm sure an explanation will come up for how you can officially prove these cofunction identities. But when it comes to the sine and tangent cofunction identities, those would be, you could prove just like we just did with the cosine, but once we have the sine and tangent sum and difference identities. But for now, we go ahead and officially put these cofunction identities into our trig identities sheet. These are true for any angle theta. All right. Note, because the trigonometric functions are periodic, the solutions in example 2 are not unique. We give only one of infinitely many possibilities. So yeah, they're talking about this example here. And we talked about this when we worked cofunction problems in chapter 2. But what they're saying there is that, so cotangent theta is equal to tangent 25 degrees. So what's theta here? Well, these are cofunction pairs, cotangent and tangent. And so what angle is complementary to 25 degrees, right? That would be so 65, right? So since 65 plus 25 is 90, and these are cofunction pairs, then the cotangent of one of the complementary angles is equal to the tangent of the other complementary angle, or vice versa. That's the cofunction identity, right? But what they're saying is that in this note here is that we know that you could take any angle that's complementary to 65 degrees, and that's going to be that's complementary, so plus or minus 360 degrees, or 2 pi. And that's going to be the exact same trig function value, right? Because that's the periodic nature of the trig functions, so that's going to be a valid answer. If cotangent of 65 is equal to tangent 25, but then cotangent of, so 65 plus 360 is what? That's 425. Well, then cotangent 425 is going to be a solution to this. And then but it's an infinite number. You could go plus or minus 360, plus or minus 360. And so that's what they're talking about in this note here. And now here we worked problems like this in chapter 2, just like this, but we never worked a problem like this because we couldn't deal with non-acute angles. 30 is acute, but this is a negative 30 is not an acute angle, right? It's only the positive from 0 to 90. Okay, and so you can think about this. Okay, what angle is complementary to minus 30? So minus 30 plus what is equal to 90? That would be 120. So it says theta is 120. Or any angle that's coterminal with 120 is a solution here. All right, and so let's go ahead and think about, I want to clear this up for you, because it can be confusing to think about the cofunction identities in terms of just complementary angles. Especially once you open the door for, you can input any angle into these cofunction identities, and then you could think about the solution as any angle that's complementary with that angle. And so the definition of complementary, the technical definition is two acute angles that sum to 90. Technically, there's no saying that, like, oh, minus 30 and 120 are complementary. I don't believe that's a technically correct math statement to make, because minus 30 can't be complementary with anything that's not an acute angle. Okay, but for the sake of the cofunction identities, the general cofunction identities, we could go ahead and use the term complementary. Even in the case of, we could say minus 30 is complementary to 120, just for the sake of these cofunction identities. And really the way you want to look at it is this. Okay, so x, y. So, okay, you have a cofunction pair. So let's say we've got an angle like this. So this is alpha. And then let's say we've got a negative angle like this. And this is beta. Okay. Now, also imagine that we could use alpha or beta or any angle coterminal with alpha or beta. So we could also do this, or this, right? In all of those cases, so let's say alpha plus beta, the way I've drawn it is, so that would be alpha minus beta, because this is a negative angle. What results in is not an angle of necessarily 90 degrees or pi over 2, but a vertical, a positive vertical, right? So no matter what, you could choose alpha with 5 rotations and beta with 2 rotations, or beta with 10 rotations and alpha with 1 rotation, whatever. Any kind of sum that you do, you're going to end up with a vertical, a positive vertical, right? And so that's the way you can look at then those angles are complementary. I think that's technically, I shouldn't be saying that, but for the sake of, the cofunction identities, that's the idea of a complementary angle, or two complementary angles, that when you sum those angles, no matter, they don't necessarily sum to 90, but they sum to some positive vertical angle. So 90 or any angle coterminal with 90. And if you have two angles that are complementary in that sense, then they apply to the cofunction identity. So they might not add to 90. They might add, when you add the two angles, you get, so what is 90 times, so 720 plus 90. They might add to give 810. Well, then they're complementary in this sense, right? So we added 120 to minus 30. We got 90. That's those two are complementary. We could have added, let's see, 90 minus 360 is minus 270. So we could have added minus 240 to minus 30, and we'd have gotten minus 270. Those two are complementary. So minus 240 here is an answer. Okay. Applications of the sum and difference identities. It says if either angle A or angle B in the identities for the sum and difference cosine identities is a quadrantal angle, then the identity allows us to write the expression in terms of a single function of A or B. Yeah, so if you have a quadrantal angle as A or B, then it's going to greatly simplify, because the cosine of a quadrantal angle is going to be 0, 1, or negative 1. And so if we come here, you can think about that, when we think about this from the standpoint of the graphs of the sinusoids, if you're really shifting, you're applying a shift to the cosine graph. And if you have a quadrantal angle, so you're shifting it by 0, 90, 180, And so what you're going to end up with, the reason why this is going to simplify to a single trig function is, well, you can see the mechanics of the actual algebra of the difference or sum formula. And so here, cosine 180 minus theta, if you expand this out with the identity, you get minus cosine theta. But you're going to end up with, when you do this with the quadrantal angle, you're going to end up with positive or negative cosine theta or positive or negative sine theta. Because so we start with cosine like this, and if you shift it like 90, you get, you're going to get like a sine, right? But this is a flipped sine. If you shift it like some multiple of 180, you're going to get back to the cosine. It could be a flipped cosine or whatnot. If you shift it by a quadrantal angle, you're going to end up with some sort of pure sine or cosine. But if you shift it by something different than 180, or than a quadrantal angle, then you get something like, it's not a pure sine or cosine. So it doesn't simplify that way. All right. Finding cosine of s plus t, given information about s and t. Suppose that sine of s is equal to 3/5 and cosine of t is equal to minus 12/13, and both s and t are in quadrant 2. Find cosine of s plus t. All right. So they expand out cosine of s plus t using the sum identity of cosine. And so here we go. Now we've got sine of s and we've got cosine of t. So we've got this and we've got this, but we need cosine of s and sine of t to evaluate this. And so what they do is, they use two different methods. So the first method is, the key is they give us this information that s and t are in quadrant 2. So with that, we can draw some terminal angles, sides in quadrant 2, and then use what they give us here to construct some the right triangle associated with the trig function definition. So they give us that sine of s is 3/5. It's in quadrant 2, so it's positive 3/5, which makes sense because it's in quadrant 2. So opposite over hypotenuse is 3/5, but we don't know x. And then similar idea we could do with we know x is going to be negative though, and similar idea here with the cosine of t is minus 12/13, right? Now with that, we can solve for this, and we don't know this side length, but we can solve for these using the Pythagorean theorem. We know x is going to be negative. We know y is going to be positive. Okay. And then now we've got the full triangles, and we can evaluate. We need cosine of s and sine of t. We could go ahead and just and get them here. And there you go. All right. Now they use another method with Pythagorean identities. So all we're trying to do is find cosine s and sine t, because we already have cosine of t and sine of s. So since we have the cosine value and a sine value, and we're looking for the sine and cosine to those trig functions, we can use the Pythagorean identity of sine squared plus cosine squared is equal to 1. But this is going to give us two possible answers. But since we know the quadrant, we can state explicitly, we can find cosine s, and same idea, we can find exactly what sine of t is and use and plug that into the identity formula. All right, so now here's a real life application. It says applying the cosine difference identity to voltage. Common household electric current is called alternating current because the current alternates direction within the wires. The voltage V in a typical 115 volt outlet can be expressed by the function. So the voltage with respect to time is this 163 sine omega t. Yeah, it's not like direct current is a constant voltage, but alternating current is, if you hooked it up to like a voltmeter, it's a sinusoid. Okay, and so this 115 volt, which I guess it alternates between 163 volts, positive and negative 163 volts, but then like the total energies, they state it as 115 volt outlet. But So omega is the angular speed in radians per second of the rotating generator at the electrical plant, and T is time in seconds. So it is essential for electric generators to rotate at precisely 60 cycles per second, so household appliances and computers will function properly. Determine omega for these electric generators. Well, yeah, so they give us the frequency here, 60 cycles per second. So that's you get the frequency by, it's one cycle divided by the period. So the time it takes to go through one cycle, you do 1 divided by that period, and that gives you the frequency, 60 cycles per second. But the omega, they're saying, is angular frequency, and so we know that when we think about the circle that corresponds to the sinusoid, when we go through one cycle, we've gone through 2 pi radians. So what you're doing is, so one cycle is 2 pi, right? So instead of doing one cycle per t, we're doing 2 pi per the period. But what is the period? Well, let's see. So 60 cycles per second. So how many seconds in a cycle? That's 1 over 60 seconds in a cycle, right? It takes, if you're going 60 cycles in 1 second, then in a 60th of a second, you go 1 cycle. So for every 60th of a second, you go 2 pi radians around the corresponding circle. So that's going to be it. So 2 pi over 1 times 60. So 120 pi radians per second is the omega. Okay, then part B, graph V in a window 0 to 0.05 and minus 200 to 200. So yeah, they're going to do a graph. And then it says determine a value of psi so that the graph of 163 cosine of omega t minus psi is the same as the original function, sine curve. Well, okay, yeah, so here there's 2 ways we can look at this, and I'm assuming they want us to go ahead and use the difference identity for cosine, but you could also look at it in the sense that if we know the period was 1 over 60, then we can apply a shift. Now, remember, in terms of, it's not just, we don't make, so if we shifted, how does this work? If we shifted, let's see, we start with cosine, and we want to shift it, so minus psi, we're going to be shifting it to the right. So yeah, if you shift it to the right a quarter of a period, yeah, because we shift this, that's a quarter of a period, then you get sine. So we just need we want to shift this to the right a quarter of a 60th. But then you would do that, though. That doesn't mean you make psi 1 over 240, because you have to factor out the omega and get t with a coefficient of 1. So you could do it that way, right? You could do it by just applying a shift. We'd have to write this as 163 cosine of omega t minus psi over omega. And therefore, we want to make psi over omega, in that case, equal to a quarter of a 60th. Because that's a quarter of the period. So 1 over 6 times 4 is 24, so 1 over 240. So 240 psi is equal to omega, but omega we saw is 120 pi. So psi is equal to 120 pi over 240. So psi needs to be pi over 2. Okay, that's one way of looking at it, but the other way is, which was what they wanted us, if this was confusing to you, go through we learned all this in the previous chapter, going through the graphs of the sinusoids and the other trig functions. But okay, but the other way they do it is they use the difference identity. So we're trying to, let's see, what do they do here? Okay, they verify that cosine x becomes Okay, so they don't even use the difference identity here. They go another route. You could have used the difference identity, but they say that, just to be creative, I guess. I don't know why we wouldn't use the difference identity. That's the point of this section. But they first factor out a negative here from x minus pi over 2 to make it pi over 2 minus x. And then with the even odd identity for cosine, that's just cosine of, you could take the minus out. And then they took out the negative because if you had x minus pi over 2, that's not, cosine of x minus pi over 2 is not sine, but cosine of pi over 2 minus x is equal to sine. Well, why did they do that? Because cosine of, it's even. Cosine of x minus pi over 2 and cosine of pi over 2 minus x are both equal to sine. I'm not sure what they're doing here. But yeah, you could have done, so cosine of x minus pi over 2. This is a quadrantal angle, so the difference identity, so cosine x cosine pi over 2 plus sine x sine pi over 2. So cosine pi over 2 is 0, sine pi over 2 is 1, so there you go. Not sure why they didn't do that, but they did it another way here. So with that, we know that if psi is pi over 2, but wait, if you shift cosine pi over 2 to the right, well, pi over 2 is a quarter of the period. A quarter of the period of the standard sine or sinusoid is, so it's because 2 pi, a quarter of that is pi over 2. So yeah, I'm not sure exactly how they're looking at this. I like looking at it the way that we talked about in the previous chapter. So, again, you factor out you get the t here with a coefficient of 1, and you factor out whatever you need to factor out, and then you look at the shifted period from that perspective. Because, right, the way I like looking at it is we're shifting the curve with omega, with the omega applied, the vertical stretching or shrinking applied, you're shifting that by psi over omega, pi over 2 over omega. But they're looking at it from another perspective where they're looking at it here from the perspective of you shift the unstretched or shrunk about the x-axis cosine first, and then you stretch or shrink it. So there's different ways of looking at it. But okay, verifying an identity, verify that the following equation is an identity. And so, yeah, we can use, we worked in the previous section, we verified identities. Yeah, 2 sections ago, we did the fundamental identities, and then in the previous section, we verified identities. But now we can verify more identities. We have an additional tool in our toolbox. We can use the sum and difference, or the sum and difference identity for cosine, or the cofunction identities now. So we'll verify some more identities using with these additional tools we have. Okay, now let's work some example problems.